All right. Thank you everyone for coming on this incredibly cold day with many other things going on as well. It's my great pleasure to have Andrew Appel from Princeton University here. So my name is Karthik Goswami. I direct MICDE, and if you've seen of late, MICDE has been doing a lot with computer science, from high performance computing to hardware, software, co-design, and AI. But more recently, we're venturing into formal verification of numerical methods in quantitative computing. And some of our faculty members, including myself, have been collaborating. So a bit more about Andrew. So he is the Eugene Higgins Professor of Computer Science at Princeton University. He has done amazing work, a lot of hard things. The hardest thing he's ever done, I cannot speak for you, is being department chair for 6 years at Princeton. Yes. So his research is in software verification, computer security, programming languages and compilers, and technology policy. He's done some work on election integrity with Alex Hunt.
Is it not working?
So you see his AB in physics from Princeton in 1981 and Ph.D. in CS from Carnegie Mellon in 1985. He's the editor-in-chief of ACM Transactions, programming languages and systems, fellow of ACM. So he's worked on many things in compilers and program verification, software verification, but also interestingly in n-body algorithms in the 80s, and foundational proof carrying code in the 2000s, and verified software toolchain over the past decade or so. So we are very thrilled to have you here, and thank you for coming.
So let's prove program's correct. What does it mean? Well, to prove a program is correct, you need a specification of what it's supposed to do. Programs that don't have specifications cannot be incorrect. They can be surprising. All right. And to write specifications, I would like to write my specifications in formal logic. So for that, you need a logic. There's many logics out there. I'll choose the calculus of inductive constructions, which is a logic pretty good. And you need a tool for checking proofs in that logic, like a graduate student. But if your graduate students get bored easily or they're not very reliable, you need a computer program to check your proof. So a proof assistant, such as Prof, now called Prof, has a kernel that's the part you have to press to check the proof. It's fairly small. It has an interactive development environment and tactic language and scripting language and so on that build proofs, help you build proofs. You don't have to trust this part because it's building proofs that can be checked by a kernel. Okay, so what does it mean to prove a program correct? Well, let me prove a program correct for you. Here's the data structure. The natural numbers, O is a natural number, and S of a natural number is a natural number. So that's 0 and successor, sort of axiomatized in logic. That's one way to do it. And here's a program called add that takes two natural numbers, A and B. If A is O, return B. If A is successor of A prime, then I'll add recursively on A prime and B and wrap the successor constructor around that. So that's sort of the specification of addition in natural numbers. Well, I claim it's addition. It's just a program. Can we prove some property of that program? Well, here's a theorem. Add is associative. That's a correctness property of the add function. I claim for all A, B, and C, add A of add B, C equals add of add A, B, and C. Now, everything that's turned green so far has been accepted and type checked by the proof checker in the interactive development environment. And now, when you state a theorem, but you haven't proved it yet, what you get is a proof state that has your proof goal. And below the line is your proof goal, and above the line is all the things you get to assume. Right now, there's nothing above the line. It's just below the line is your theorem statement. And if I apply a tactic like intros, introduction of the for alls, we now see that A, B, and C are natural numbers above the line about which we know nothing except that they are natural numbers, and we still have to prove the rest of the quantified statement. Now, how do we prove a statement like that? Well, by induction. Should we do induction on B, or induction on C, or induction on A? Well, You can try any one of them, but the one that will work tends to be the one on which your program is recursive. So let's try induction on A. All right, induction A. Here's the rest of my proof. But the green part is what has been accepted so far, and so my proof state is about the part of the proof right here. And you see now there are two things I have to prove. I have to prove the base case, and I have to prove the inductive case. So the star lets us focus in on the base case, and if we simplify this, simplify will unfold add O and do the pattern matching of the cases and give us back the argument, which was in this case add BC. So if we simplify the left, we get add BC, and if we simplify the right, we get add BC in the base case.
It's not the most moving.
Yeah. Okay. And a thing is equal to itself. That's the property of reflexivity of equality. So let's use the reflexivity tactic. Reflexivity tactic. And that goal has been solved. And now we're in the second sub-goal, which is the inductive case. So let's simplify that. So this simplifies down the add SA here and the add SA there. So now that's my proof goal, and I try reflexivity, but this fails because the left-hand side doesn't look exactly like the right-hand side. And a very important property of the proof assistant is not only it should accept correct proofs, but it has to reject bogus proofs. So this is a feature that this failed. All right. Well, how am I going to get the rest of the proof done? I have an induction hypothesis. IH stands for induction hypothesis. It's the induction hypothesis about A. And it says this equals that. So I can rewrite by IHA, and it'll replace this by that inside the S. So if I delete my reflexivity and rewrite by IHA, I get a thing that's equal to itself, and I can say reflexivity. And this now is defined. This theorem is added to my library of proved theorems, and I can use it in the proof of other theorems. So that's how program verification works. Little add functions that are pure functional programs on the natural numbers. So now let's scale it up to C programs that work on floating point numbers. How hard could it be? Okay. Now, when we do this, we're going to do it in modular layers so we can get separate subproofs that tie together. Typically, people, when they do program verification, they want to prove that your C program implements correctly the functional model of the algorithm. And we might express the functional model as a pure functional program in some abstract logical language. And then we want to prove that the algorithm actually solves the problem it's supposed to solve. That's a separate proof. And we want to prove that the program correctly compiles to machine language. And if you can compose all these proofs together, you get a proof that the compiled program solves the problem you wanted it to solve. And if you've proved each of these in the same logic, in the same proof assistant, then you can compose them together into that single machine-checked theorem. But at each level, you use different proof techniques and different libraries within the proof assistant. So to prove that the program correctly implements the functional model, I use a library that I developed over more than 10 years called the Verified Software Toolchain. To prove that the program correctly compiles to machine language, I compile the program with the ComCert Verified Optimizing C compiler, which is proved correct with a proof in the same logic. But to prove that the function model correctly implements the high-level spec, we have to use the mathematics of the application domain, and it's different in every different application domain. So first, let me talk about this middle layer. Verified Software Toolchain is a program logic for C. You know what for logic is, with preconditions and postconditions and loop invariants. Well, it's a kind of for logic. It's embedded in the Clock Proof Assistant. It's proved sound. What that means is, if you can prove something in the program logic about your program, and then you run your program in the operational semantics of the programming language, then it will actually have that behavior. And that's a theorem that we proved once and for all in Clock. So now whenever we use program logic, we can leverage that theorem. Unlike traditional 20th century Hoare logic, it's a separation logic, so it handles pointer data structures and object-oriented programming patterns that you might roll your own in C. And it has a proof automation tool, programmed in the scripting language of the proof assistant to help you apply the program logic to your program. Okay. Then, depending on what kind of thing the program was supposed to do, we need to prove that the algorithm that it's implementing, that we prove that it implements, correctly does something useful. And other people have had great success doing that in the area of compilers and operating systems. I've done it in cryptography, in databases, in networks, data structures. So here's an example of a theorem that we proved a few years ago. The cryptographically strong random number generator, that's the most widely used one, standardized by the National Institute of Standards and Technology, called MICDE, gives you strong randomness. What does that mean? It means that the open source C program that you can find in Embed TLS correctly implements the NIST standard. We proved that using VST. And that, if you run it, the attacker who does not know your random seed has a chance of guessing the next bit. Well, if the attacker can do no more than 2 to the 100 steps of computation, then their chance of guessing the next bit is no better than 0.5 plus 2 to the minus 70. That's a standard kind of cryptographic proof from the 1990s, but we were able to implement it in the proof assistant. And I don't know anything about cryptography. Matt Green at Johns Hopkins is our cryptographer. He doesn't know anything about program verification, right? And the students, Catherine and Nafat, did the verifications in COP of these different advice from the people that knew about formal methods and people that knew about the application domain, in this case, cryptography. There's another theorem, verified erasure correction. So the Reed-Solomon coding is a way of, you send your network packet, you send 6 network packets, but actually send 3 more that are cleverly designed so that if any 3 of these 9 packets go missing, you can reconstruct the missing ones without having to ask for a retransmit. Okay, and so it's a C program, and it's a mathematical abstraction about the field of primitive polynomials, and so the upper layer is finite field math, and the lower level is C programming, and in this case, the students, Josh and Shinshi, are experts both in the math and in the program verification, and all I had to do was just watch. So that was a nice result. Okay, so now let's do this in a different application domain, numerical methods for scientific computing. And I'm going to talk about 2 case studies that we did. One is in differential equations. So, you have a differential equation, and maybe you can't solve it in closed form, so you simulate it with time steps. And the other one we did was solving a linear system, AX equals B, for a large, sparse matrix with a heavyweight diagonal. So let's do one at a time. This is, all right, here's how it went. Here's our differential equation. These 2 equations for momentum P and position Q for a harmonic oscillator. And if you took physics, you might remember you can do this in closed form. Forget that you knew that. Let's pretend we don't know how to do this in closed form. Okay, so we integrate it by integrating the time step. N is the number of time steps we've done so far. H is the size of the time step. We have a struct that holds the state with, momentum and position. And we calculate this thing in each time step and add H to the time. And we want to prove that this program finds an accurate solution to this. We can't prove it's correct in the sense that it finds an exact solution, because it doesn't find an exact solution. So here's our specification at the high level spec. Here's a specification of what it would mean to be correct. That if I have P and Q that's the exact solution to this harmonic oscillator system. And so here it says that I have the exact solution here. Here's the floating point solution that I computed with the functional model of my algorithm. Here's the difference between them, and I want to prove that that's less than my accuracy bound. Right? So this is my specification of what it would mean to be correct. But that's a specification in the language of the functional model. What I have is a C program that uses data structures. So what I need to prove is that the representation of this functional model in the data structures of the C program computes to an accurate solution. So this is a specification, what a specification of pre and post conditions look like in the Verified Software Toolchain's specification language. Okay, and for this one, we're using N is 1,000, accuracy is 0.0308. We're doing it in single precision floating point. Now, where do the bugs come from and the errors? There's three sources of inaccuracy here. One is we're using discrete time steps instead of an infinitesimal delta t. Two is we're not computing in the real numbers, we're computing in floating points. So when I multiply two floating point numbers, there's a little bit of bits that fall off the end from round off. And three is I might have bugs in the program. I'm going to address each of these and compose together the proofs about each of these into a single main theorem. So here's the proof outline. Here's the C program. Here's the floating point functional model. Here's the real value functional model. Here's the specification of a harmonic oscillator. And here's the proof that relates these two together. Here's the proof that relates these two together. Here's the proof that relates those two together. And here's like the main theorem. So let me go through this bit by bit. Here again is our C program. Here's our floating point value functional model, expressed as a pure functional program in the logic, where this times here is floating point multiplication, and this add is floating point add, and we can prove in, using the verified software toolchain that this C program exactly implements this functional model. All right. Now, discretization error. I have a delta t instead of a dt. Now, Euler's method, which is very old, is pretty bad. Once it's stepped away from the curve, it keeps stepping further and further from the curve. So use a second order method, the leapfrog method. We integrate the acceleration we use in this period, we add with the velocity that we use in this period. So we overlap changes in velocity and acceleration, and that turns out to be much more accurate. It still has discretization error, but it's an order of magnitude less. So we can implement the real value functional model, which is the expression of this algorithm, like so. And here's the true solution. And you can look in a numerical analysis textbook and find how do you prove that this leapfrog method accurately approximates the differential equation. And we call that the local single-step discretization error, and then we're going to compose that over many steps. So here's the theorem about local discretization error. It says if the time step h is less than 4 and omega, to keep things simple, let's say omega equals 1, easy to generalize, then the error is less than h cubed times the absolute value of the magnitude of these values. Okay, and the proof is, well, expand the ideal solution of the harmonic oscillator of the Taylor expansion using the Taylor underscore Lagrange theorem. So the first part of the sentence looked like math, but it starts to look like software because this is an actual theorem in the library. And it's in this library that's named copy code. So this is math, but it can be done right there in the logic of the proof assistant. Okay, that was here. What's next? Floating point roundoff error. When we're starting to do this, I said, maybe there's some tool somebody has written to do floating point roundoff error. And I found lots of tools, but I wanted one that integrated well into the proof assistant. And that's going to relate, take the same formula in real valued and in floating point notation. And I want to relate semi-automatically or as automatically as possible what error I get from computing this entire formula, not just one operation. There are lots of tools for this, as I said. But I want one that is fully integrated into the proof assistant. So I Googled, and I found this paper that had been written a few years earlier, and then abandoned with an open source GitHub repo. Well, I love an open source GitHub repo that's documented by a reference. What could be better? So it took a week or two to bring it up to date with the latest version of the proof assistant and the compiler and so on. And then we added lots of features to it and published our own paper about the enhanced version of the VC float tool. But basically, its job is to calculate a bound on round-off error in some set of formulas that you might be using. Okay. So from the premise that P and Q are bounded by minus 1.0041 to plus 1.041, then the proved error is really tiny, 10 to the minus 7. Could be better, but we're using single precision floating points, so that's why it's better. Okay, so that was this one, local round-off error. Now we want to prove global, meaning that over many, many time steps, the round-off error is not too bad. These bounds are required by, the tool. Otherwise, if these bounds were bigger, then this number would be bigger. Now, ideally, we have one set of theorems that relates this to this, and a different set of theorems that relates this to this, and another theorem that relates this to this, and they're all modularly separate from each other so they can be maintained like we want to maintain software in a modular way. But unfortunately, that theorem about round-off error relies on P and Q not growing too large. But if you don't know how much round-off error you have, then maybe P and Q will grow too large. So we have this sort of snake biting its tail, unfortunately. I can claim they shouldn't grow too large because the harmonic oscillator conserves energy. And you might be able to prove that it conserves energy even if you couldn't solve the differential equation. But it only conserves energy in the real numbers. There's no guarantee it conserves energy in a floating point. So we need to prove that the sort of spectral radius of the matrix is not so big so that no matter how many times you compose it, it's still going to be within those bounds. So we means, of course, my student, she proved all these things and figured out what it is we need to prove. And so it worked. Okay, so we proved this matrix norm bound, which turned out, unfortunately, to be necessary to prove that with local, that we can prove our local round-off error. So now I've shown you everything that's outlined in red. These three we can get by adding up the errors using the triangle inequality. So that's really easy. And finally, how do you compose the theorem that the C program correctly implements the functional model with the theorem that the functional model solves the problem to get the main theorem that the C program solves the problem? We use a property of the verified software toolchain called fun-spec subsumption, and it allows us to compose these two proofs, get a theorem that the C program computes an accurate solution to the ordinary differential equation. So there we are. That was case study number 1. Case study number 2. This was done at the University of Michigan mostly, with some help from us at Princeton and at Cornell. You have a matrix A and a vector B, and you want to find some x such that AX equals B. And the matrix A has some properties. It's sparse. Sparseness isn't necessary for this algorithm to work, but it's the motivation for using this algorithm because this is a way to solve for x without converting the matrix. And it's very fast, especially if the matrix is sparse. And the diagonal elements are large compared to the off-diagonal elements. The Jacobi method, which is, well over a century old, I think by now, you separate the diagonal from the rest of the matrix, and basically you keep multiplying by the rest of the matrix iteratively, normalized by the diagonal in some way. And there's a classic theorem that you can find in the textbook that says it converges. If the matrix A is diagonally row dominant, that just means that the diagonal elements are big and the off diagonal elements are small. Then this converges within to tolerance tau within a certain number of iterations. It's just an easy function of the diagonal dominant and tau. Okay, but I don't have any computers that can calculate in the real numbers, right? We have floating point. So here's a theorem, very useful from a textbook 30 years ago, that in floating point, it converges. But that theorem ignores overflow. It ignores underflow. It doesn't worry about program bugs and sparse matrix implementation. Sparse matrix implementation is a data structure. And your C program is implementing some data structure that's simulating a dense matrix. What if you get it wrong? Okay, so this is great, but here's what we proved. That the C program that operates in floating point that, like any real life floating point, has to worry about underflow and overflow, converges within, some number of specified iterations. I just left out the formula for it. With the proved absence of overflow, tolerating underflow if it occurs, which necessitates, a sub-theorem, the proved correctness of the sparse matrix implementation, all with end-to-end machine-checked proofs. Okay, so to an accurate result. To do proofs like that, we don't want to start from scratch. It really helps to be using tools and libraries. So I talked about this tool already, the Verified Software Toolchain. That gets us from C programs to functional models. Block is a library developed in France a dozen years ago. That's a formalization of the IEEE floating point standard down to the bit level. And from the axiom that your computer implements the IEEE floating point, you can use theorems proved in Block and in these other libraries to do math about floating point. The interval library does automation of interval arithmetic proofs that bound numbers and formulas on numbers. Valid STP is a library for semi-definite programming for proving that your Cholesky decomposition that tests whether your matrix is positive definite really will guarantee that your matrix is positive definite. BC float I already talked about. It's for automatically computing round-off errors in formulas, floating point formulas. BST Live connects some of these tools to actual C program libraries in math.h. LA Proof is a package for LAPACK. LAPACK is a traditional linear algebra library with things like matrix vector multiplication. And here is a version of that library with accuracy and correctness proofs. Indeed. So there's a paper about it and an open source repo. And what could be better than an open source repo that's accompanied by referee paper? And what we will be working on next is, let's take this bottom-up idea of we have proofs about matrix vector multiply, we have proofs about linear solvers. Let's build it up into bigger libraries, initially for linear algebra, and then eventually maybe for differential equations. So if you want to parallelize this algorithm, you might take a block diagonal matrix, and on each CPU, each processor, you solve for the block. And so here's, what you do is you have 5 processors. If you have 50 processors and a really big matrix, you make block diagonal matrix of 50 blocks. And this is not a bad algorithm. It has sort of data locality in converting these blocks. And it makes more progress in each iteration than the standard Jacobi because the blocks are bigger and there's more for it to work with. So there's less communication. And we're going to use Cholesky decomposition of the blocks so that we can sort of invert them, solve and back substitute for the blocks as we go. And for Cholesky decomposition to work, the original matrix had better be, or at least the blocks have to be symmetric and positive definite and large, because we're using Jacobi iteration. So this is really for a special case, a useful special case, but we will need other linear solvers to handle other cases that use other algorithms that are also proof correct. So the block Jacobi algorithm solves the linear system, and we will prove it correct and accurate and convergent. And by we, I sort of mean like the student, sitting over there, or me. And then we'll have a parallel implementation of block Jacobi, because I mentioned that the verified software toolchain can prove things about the correctness of parallel programs. I've already proved the correctness of a parallel dot product algorithm just as a warm-up. Parallel dot product is not actually all that useful. We'll prove things about the correctness and accuracy of the Cholesky decomposition of the diagonal blocks into an upper triangular matrix whose, when you multiply the transpose of the matrix by the matrix, you get the original feedback. But doing Gaussian elimination on triangular matrices is easy. That's why we do this. The off-diagonal matrix, we will use the compressed sparse row representation and algorithm for matrix vector multiply. That part is already proved correct. We can use mixed precision. What is mixed precision? Well, single precision, double precision. In the old days, meaning before 2020, let's say from 1950 to 2020, the manufacturers of supercomputers knew that their customers were people like Karthik doing scientific computation, computational science, and those people wanted 64-bit floating point. So by God, those supercomputers had 64-bit floating point. In 2010, the manufacturers of cheap desktop supercomputers knew that their customers were gamer bros in their mother's basement, and the computer graphics had to look good, for which double precision wasn't absolutely necessary, and it didn't even have to be all that correct. And now, those companies know that their customer is the one training a machine learning model. And it turns out in training machine learning models, 32-bit precision is more than you need usually, and 16-bit precision or 19-bit precision is pretty good. So you can't rely on that the supercomputers of next year will have fast, efficient 64-bit floating point. So what you want is proofs about programs that use lower precision than you're used to. In the old days, you didn't have to prove it. You just use 64-bit precision, which is way more than you need, so probably you could get away without proving it. How does that apply to this algorithm? Well, it turns out that the computationally expensive part is solving the individual blocks on the individual CPUs, and the computationally cheap part is the sparse matrix vector multiply of all the rest of the matrix by this vector. And it turns out that if you do this part in single precision floating point, take the expensive part of your program and do it in single precision, and you do the cheap part of your program in double precision, you get a result that's accurate to double precision. Just turns out that way, and you can even maybe prove it. And the reason it turns out that way is that these things end up just being a correction to values you get here, and these have small magnitude when you solve for their inverses. You're adding small magnitude single precision numbers to large magnitude double precision numbers. So it works out. All right. So we didn't need mixed precision 20 years ago because double precision went almost as fast as single precision on your Cray 2, for those of you that had one. But now, okay. So ideally, we could apply this linear solver to some application in a differential equation for fluid dynamics, right? At each time step, we solve a bunch of linear systems. And what we want to prove is the main end-to-end theorem that this accurately simulates the fluid dynamic equations of interest. But that, we're not nearly there yet. And if we do that, we would have a top-to-bottom proof that some C program finds a correct and accurate enough, we can quantify the accuracy, solution to some interesting scientific problem. And we do this in a modular way and make each of these bullet points a proof that's sort of independent of each of the others, then we can mix and match and remix and compose these theorems and subprograms in ways that are useful in other applications. Okay, so in other application domains, machine check correctness verification and correctness verification. I'm not verifying just that the machine doesn't crash, or the program doesn't crash. I'm verifying that it solves the problem of interest, that there's a functional specification of how its output is supposed to relate to its input, and it does that correctly. And there have been great advances by other people in those areas. So there, there's the CompCert proved correct optimizing C compiler, which is amazing. That by the end of the 20th century, we knew that that would never be possible, but it turns out to be possible. And the first realistic operating system microkernel correctness proof was done in Australia in about 2009 in a collaboration between the domain expert who knew a lot about microkernels and not much about formal methods, and the formal methods team that knew a lot about formal methods and had to be taught about microkernels. I showed an example in cryptography. There are other people doing lots of successful things in the verification of cryptographic software. Distributed systems has long been a field where there's been successful applications of formal verification. And it's particularly motivated because it's so hard to get distributed systems right in the first place. And I claim that formal verification shows promise for scientific computing, but so far only promise, not so many big results. I've shown a couple of little results that are feasibility studies for what we might be able to do. And that.
What a great talk. And I think for everyone's information, there is just a very rich range of problem setting of verification we can address, both from the comfort level, having achieved verification, but also, as you said, a mixed precision setting where we can enhance efficiencies. So anyway, I want to open up to the floor. I have a few questions, but I want to see what the audience has in mind. First, go ahead.
So for scientific computing, is the arithmetic the main problem, like the round-off errors and reasoning about or are there like other problems?
Well, okay, first of all, I'm not a scientific computing expert, so I only pretend to be one when Karthik is not standing up. But traditionally, the method error, like discretization error, could be considered the bigger problem, or the program bugs. And because you had plenty of precision in your floating point, 64 bits, the roundup error is there, but you could hope that it's dominated by the other errors. You didn't have to worry about it all the time. That's my understanding of the way things used to work. And why do we want to prove everything all together? Well, as a formal methods guy, I like the idea of an end-to-end theorem that doesn't neglect anything. And we couldn't do those proofs on pencil and paper. They're just too tedious and too hard to keep track of all things. But you get from mechanized tools the ability to keep track of everything and make sure it's done. Yes.
For the ODE example, you had a problem with the closed form solution, but still improving that the numerical method worked. You had to do some sort of normal math, right? There was that one result that your student had to prove. And I'm curious if you think for more complex problems, the complexity of that proof step will grow. So
right, that was pretty simple. It was two variables, not 12 or 100. It was second order, like the leapfrog method, not the Euler method. So not quite as simple as the first order. And I thought a little bit about what it would take to scale up this technique to lots more variables and higher order. And I think what you would want to do is start with existing tools that take the specification of your differential equation and automatically generate the C program that does, the 8th order method with some appropriate time steps. And prove things about the correctness of those tools. Either you make a version of the tool that's proved correct a priori, or you make a prover that can take the output of the tool and relate the C program back to the differential equation. And, if I just had one 8th order 10 variable problem to do, then I would just do that. But if I thought there might be more than one, then this tool-based method would be the approach to take.
And if I may add, at least for certain classes of problems, you don't need the exact solution to prove that it will converge to the exact solution as you.
In this theorem we proved, we did not need the closed form solution. We did not use the closed form solution. What we did was prove that the result is close to a solution. We find the solution in closed form. We did reason about what happens in one time step. That's not the same as the closed form solution over many time steps. So we didn't actually cheat in that way.
Yeah, in HP and then in the back.
So you already answered one of my questions, but I will ask the other one. How easy is it to do this for PDEs instead of ODEs?
I don't know. I'm not in America.
Not a huge stretch, because ultimately many of these tools transfer. But when you go nonlinear, then the topmost part of his flowchart, that it gets harder, but everything else can still be done, the functional proof. But I don't think there is anything particularly different about PDEs. Because ultimately, they discretize a PDE or an ODE, they're all a differencing methods as far as the computer sees it.
What are the largest barriers to more widespread use of formal verification by practicing computer systems designers?
Well, we have to teach it. We have to build tools that work for them. The tools I like to use are extremely expressive, meaning the logic is powerful enough to say all the mathematical things you might want to say. But those logics, A, they're a little harder to learn how to use, and B, they have far fewer automatic decision procedures that sort of, right? So there are other tools out there that have less expressive logics, but have a lot more automation. And the programmer can just write down the invariance in a logic that looks a lot like the source language they're already using. And those systems already find proofs that the loops preserve the invariance, or sort of tell you something about where they fail, and where you need to add more clauses to your invariant. So I think there's been a lot of progress in making more usable tools, and to me the challenge is to either scale up the expressiveness of the easy to use tools, or make the expressive tools easier to use, or somehow meet in the middle.
So two questions. One, relating, I guess, to the adoption of formal methods. It's like the mathematicians and the lean people are all big on LLMs these days, and there was like the Terry Tao stuff and whatever. There's a lot of energy around that. I don't know if I buy personally, but do you have thoughts on like the notion that large language models can reduce that barrier to entry to formal methods, or does that just reduce to another sort of like, oh, we just wrote our spec a different way? And then second question.
Let me answer the first question. I think there's a lot of promise in the following way. We know that you can't actually trust an LLM. It'll hallucinate all sorts of stuff. If I write down a theorem statement and the LLM finds a proof that the kernel of my proof assistant checks and says, yes, that's a proof of the theorem, then I don't care what it hallucinated. Well, I care a little bit. Those are going to be little hard to maintain as if I rerun the LLM tomorrow, it might not find that proof. But at least the idea that there's a notion of a theorem and a proof, and you don't have to care so much who found the proof, if you can check the proof. That's a notion that goes back now 90 years, like 1931. And there's even a whole DARPA program funding people all over the country to work on, it's called Provers, funding people to work on, using AI, including LLMs, to find proofs, in proof assistance like this of theorems that the human gets to read and specify. So yeah, that could be very promising, but it might not work.
But then,
Second part.
yeah, second question. You alluded, I think, a little to the choice between focusing on like certified implementations, kind of whatever your tools or your methods or whatever, fully sort of certified end to end and built in those platforms, or sort of certificate that you can generate at the end that external answer is correct. Do you have thoughts on when choosing research problems or when each of those approaches is most suited, or do you not see that as a
if your algorithm is very complicated, but the certificate checker is simple, then it will certainly be a lot easier to prove the certificate checker is correct. And especially if the certificate checker runs fast. Okay, so for example, the ComCert verified optimizing C compiler, all the phases but one are written in this proved correct period way, but the register allocator, they use the George and Appel iterated register coalescing algorithm, and they run that in an unverified language. And the certificate checker, the result is that no two values live at the same time are assigned the same register. And you can check that fairly easily without rerunning the whole algorithm. So that's what they do. It's perfectly valid. If your problem breaks down into, you can write a checker to test every result. It still wouldn't tell you one thing though. Like, we go back to the linear solver. Where was it? If I run this and I get a vector x, I can test whether it's a solution. So why did I need a proof? Well, the proof is that this will converge within a certain number of iterations. So, if you're worried about that after you've been, you've gotten to the 7,000th time step of your differential equation, and there's a linear solve that diverges. You wasted that many hours of supercomputer time. This will tell you something. Question?
I was kind of related to questions on like tool chains. I'm curious, like with the tools like LA proof and the other ones you mentioned, like if I have some like I guess linear algebra heavy algorithm or program, I'm curious how easy it would be to like if you have I guess some formal methods background but not a ton to like use those tools to put together an algorithm that would be like verified.
Well, let's see. LA proof, I would call it a library more than tool. It has sort of two parts. One is the functional model of floating point matrix vector multiply is this accurate. And two, this particular C implementation of sparse matrix vector multiply faithfully implements that functional model. Now, how might you use this? Well, you might say, I don't like your C program, I'll supply my own. Then you just have to reprove the bottom part. So that takes some training. But basically, if you take a one semester course in software foundations using COP, by the end of it, you can get to the point of being able to verify simple C programs like that. Or you might say, yeah, I'll just use that C program. But of course, matrix vector multiply isn't your entire program. So now you've got the rest of the program, and you either start proving that correct at both levels. Now you got to learn how to do the upper level proofs and the lower level proofs. Or you find a buddy who's willing to learn the upper level proofs, and you concentrate on the lower level proofs, and that division of labor works very well. Or you have the unproved part of your program, but at least you can rely on the library that you're calling. So there's no perfectly easy solution, but the division of labor does work. Yes.
In the talk, you have been mentioning the difficulty improving the floating point computation part. So I wonder if in other kinds of program that or have you encountered any like techniques to automatically identify the floating point part of the program or system, and then like skip this part of component to prove by replacing it with some real number of parts?
Yeah, that's pretty easy to do, right? I have actually coded up sometimes the program that takes the floating point program and extracts from it the version of that program that would work in the real numbers if you could compute in the real numbers. So I can automatically calculate the real value floating point model from the floating point functional model. There was a slide I showed with both of them. And when this one multiplied, that one multiplied. When this one added, that one added. And if you're pretty sure that floating point round-off error is not going to be a big source of inaccuracy, and you're just worried about method error, discretization error, and so on, then you could use such a tool, and it's a pretty simple tool to build. Yes.
So if you were to apply this sort of framework to a more complicated scientific computing problem, what sort of problems would you expect to find and then be able to solve?
Well, so the first rule when you're a formal methods person working in the application domain is to refer those questions to the experts in the application domain, whether it's cryptography or scientific computing. But what we've been discussing is, this story of the drunk who was searching for his wallet under the lamppost. Not that he lost it there, but the light's better there. So we're going to build bottom up some.
You want to show that flowchart? It's actually very, very nice.
Which one?
One where you had the high levels.
Oh, yeah.
No. The linear one. Where you started.
Whatever. We build up a library of verified linear algebra components, linear solver components, not just Cholesky decomposition for symmetric matrices, but LU decomposition, parallelization algorithms using barrier synchronization, not just Jacobi iteration, but conjugate gradient. We can follow the structure of existing scientific libraries like PETC to see what components to build bottom up but verify. And then we can see, what kind of differential equation solvers can we verify that need to, in each time step solve 10 different linear systems. Do more case studies to get this to a scale where it becomes convincing that this will really work. Right now, it's convincing that this maybe could really work. Yes.
Are you still interested in any n-body algorithms?
That's an n-body expert right there.
Well, okay. Once upon a time, in 1979, I was a physics major as an undergrad, but I knew I was going to be a computer scientist, and I took the algorithms course where we learned about divide and conquer algorithms and tree data structures. And that was a time that physicists hadn't learned about that stuff yet. And in physics, I learned about the monopole moment and the dipole moment, and gravity doesn't have a dipole moment, and the quadrupole moment is small. So put all those together and you get an asymptotically fast algorithm for n-body simulations. And that was my undergraduate thesis. And the paper that resulted from that thesis has more citations than any other paper I've written. Some of my books have more citations than that. And then between 1983 and 2020, I didn't do any numerical analysis or numerical methods, and then I got interested in this again. But, my neighbor in Princeton, who is an astrophysicist, says that they still use tree codes of that general kind.
in doing cosmology. It gets more complicated. And they have bigger computers and it's got to run in parallel and they want accuracy bounds better than what I can do.
Any other questions? Fantastic talk. So if you're more interested in this topic, I think maybe early summer, we might hold a workshop on formal methods for math and scientific computing. There'll be a non-AI part and then there'll be an AI part. So yeah, we'll be in touch. Thank you for your participation and thank you.